We present inferring hybrid neural fluid fields from videos. Fluids are ubiquitous in our environment, such as air, water, steam, smoke, or clouds. While we are visually familiar with fluids, how to recover fluid motion from visual observations remains an open problem. The challenges come from two aspects. First, fluid is usually shapeless, monochromatic, and semi-transparent. This leads to visual ambiguity in using traditional tracking techniques. Second, the complex fluid dynamics lead to high-frequency turbulent features in fluid motion. In particular, the vortical or rotational motions are difficult to capture. To address these challenges, we need to incorporate appropriate physical priors into computer vision techniques. Many fluid systems can be described by the incompressible Navier-Stokes equations, including the momentum equation, which describes how velocity changes due to pressure, viscosity, and external force, and the mass conservation equation, which states that the fluid velocity should be divergence-free, such that substances in the fluid flow do not emerge or disappear. In this work, we propose hybrid neural fluid fields, or HyFluid. We incorporate physical priors in neural fields to recover fluid density and velocity from sparse multi-view videos. To achieve this, we propose a set of novel physics-based losses to couple both fields and use differentiable rendering to receive supervision from videos. To model rotational velocity, we introduce vortex particles to represent velocity fields, which is based on the curl form Navier-Stokes equation. Our physics-based losses include three components. The first component is the density loss, which states that the velocity field should accurately evolve the density field over time. The second component is a projection loss, which ensures mass conservation by solving for the pressure in a global space. A projection solver implements a Helmholtz decomposition by solving a global linear system for pressure and projects the velocity field to a divergence-free manifold. We also have a laminar regularization loss, which avoids trivial solutions. In laminar flow or steady flow, it is visually ambiguous to perceive any motion, and all partial derivatives regarding density are zero, which means that zero velocity can incur zero density loss and projection loss. Therefore, we encourage high-density regions to have non-zero velocities. Finally, to model and capture the intricate vortical velocities, we introduce vortex particles and decompose our velocity field into a base velocity and a vortical velocity. This is motivated from the curl form of the Navier-Stokes equation, and it allows us to model rotational velocity more accurately. To provide supervision from videos, we incorporate a rendering loss by volumetric rendering, similar to NeurIPS. Our final loss comprises these four losses, including the rendering loss and the three physics-based losses. Here we show an in-the-wild example. We capture the fluid smoke in an uncontrolled environment with three views. We show the inferred 3D fluid density field, as well as the 3D velocity field. Our approach can be used for several applications. Given input videos, we can reconstruct and visualize the velocity fields. The reconstructed velocity field also allows resimulation with different fluid materials and renderers. Since our approach also reconstructs density and color, we can compose the reconstructed fluid into new dynamic 4D scenes. Here we show resimulation results in a novel test view. HyFluid gives better resimulation results, demonstrating that the reconstructed velocity is more accurate than baselines. We also implement a fluid simulator to evaluate future prediction. Our method can better simulate the future evolution due to better velocity recovery. Thank you for watching.